All right, now this is better. So Josh, to figure out how many rockets we need to strap to the Power Wheels to jump at 30 feet over the creek, what are the variables that we know, and what are the variables we're trying to solve for?
So the goal is 30 feet over the creek. So
yes.
That would be the known.
Yes.
And the unknown would be the speed, but we have to get the Power Wheels to make that 30 feet, right?
That's exactly right, Josh. Now, another important variable is the angle of the ramp, right? Now, what angle do you happen to know is going to give us the furthest distance with a fixed velocity?
About 45 degrees?
That's exactly right. Now, I played with the Power Wheels already. We can't quite do 40 to 45 degrees. It'll actually veer off if the angle's that steep. 30 degrees is the most we can do, so we're going to fix the angle of the ramp at 30 degrees. But before we do that, let me go ahead and draw a schematic of what we're trying to do.
Okay.
So we've got one creek bed here. We've got the water here. We've got our jump here, which has an angle of theta, which we know theta is 30 degrees, as we discussed. Our Power Wheels is here, and it's going, we'll call V naught, its initial velocity. It's got a term in the x, V naught x, and it's got a component in the y called V naught y. It's going to jump, land somewhere over here. We're going to call where it lands x final, the final distance, and we're going to say where it takes off is x naught. We're going to say x naught equals 0, so that's where it takes off. We're calling that 0. And when it takes off, we're going to call the time t0, and when it lands, we're going to call the time t final. Okay, so we're going to start things looking at the x direction, which is the horizontal, and the y direction, which is the vertical, okay?
Okay, you're starting to make my head hurt.
All right, Josh, look, I'm going to keep this simple, I promise. So let's first look in the x direction. What is the component, what is the speed in the x direction in terms of v naught?
So the component would be the x arrow.
That's exactly right, this little component right here. Okay, so to get that, it's pretty simple. We're just going to take v naught x equals cosine theta. That's all we do, times v naught. This gives us this component here. Okay, now what we want to do is derive the motion equations in the x direction. Now let's first think about what is the acceleration in the x direction, ignoring wind resistance.
Well, I'm assuming if we're ignoring wind resistance,
yes,
then velocity is constant, so acceleration is 0?
So exactly, Josh, that's exactly right. So if we want to get the motion equations in the x direction, what we're going to want to do is we're going to start with the acceleration, which we're going to call a equals 0. Now if we integrate acceleration over time, what we're going to get, since acceleration is 0, is we're just going to get a constant. I'll call it c. It turns out this constant is just our velocity, which I'm going to call v naught. Okay? Now to get the distance as a function of time, we're going to integrate our velocity v naught over time, and we're going to get v naught times t plus another constant, I'll just call it c, and that constant is x naught, which we know is 0, so we're just going to put this to 0. So what we have here is we know our speed, our velocity of function of time is just constant v naught, and we know our distance as a function of time is simply v naught times t. So we have our equations for the x direction motion. Now, what do we know about the distance in the x direction from our knowns?
So we know that x is the 30 feet.
Yes, so exactly. When it lands and t is final, we know that that's 30 feet, right?
So we know if we know how long it's in the air, then we can solve for the equation and get velocity.
That's right, Josh. So exactly. So we know x equals v naught t. We know at t final, x is 30 feet, right? Mm-hmm. So if we knew, for example, that t was 1 second, for example, we could then solve for this, and we know v naught would be 30 feet divided by t, which is 1 second, which would be 30 feet per second. So that tells us if we knew it was in the air for 1 second, we need 30 feet per second to get us 30 feet. Okay? Now, to get time in the air, we're going to have to actually solve some equations in the vertical direction, right? So let's think about what the acceleration is in the vertical direction. Okay, so again, ignoring wind resistance, in the vertical direction, once this thing takes off, what is the acceleration?
Gravity?
So exactly, Josh. Unlike in the horizontal direction, in the vertical direction, our acceleration is not 0. It's actually gravity, which at the Earth's crust is 32 feet per second squared. So looking in the y direction here, we know that acceleration in the y equals g, which is, like I said, 32 feet per second squared. And we want to integrate this, ay, over dt, and this is going to basically equal g, gravity, times time plus a constant. It turns out this constant is v naught y, okay? It's our initial velocity in the y direction. So we have, and this is of course equals velocity as a function of time. So now we want to integrate velocity of time over time, and we're going to get g over 2 times t squared plus v naught y times t plus another constant. Now this constant is going to be y naught, which we're just going to say is 0. It starts at a height of 0. So now we have, and this is our equation for height in the y. So we have an equation for y of t, and we have an equation for v of t in the y direction. So what do we know about the height of the Power Wheels when it lands?
It's 0?
Exactly, Josh. So let's go ahead and plug that in, right? So we know that y of t, tf, t final, equals 0. And this equals g t final squared over 2 plus v naught y times t final, okay? So we have an equation here in terms of v naught y and t final. So v naught y, the components, it's the component velocity in the y direction. It's simply v naught times sine theta. So we have something here, an equation here in terms of v naught and t final. Now here, as we discussed before, we have the x as a function of time in the x direction. So if we plug in, what is the distance at t final? How far did it go when it lands?
30 feet.
Exactly. So we're going to say x of tf equals v naught, and this is actually in the x direction, times t final, okay? And we know v naught x is just cosine theta times v naught. So we have, and this equals 30 feet as we discussed. So we have two equations with t final and v naught and two unknowns. So we can actually go ahead and use these two equations and solve for t final.
I don't know, man. You've lost me here.
Okay, so we can then go ahead, solving for these two equations, we know theta is 30 degrees, we have again x final is 30 feet, we know gravity is 32 feet per second squared, we plug all these in and we end up getting a time in the air, a t final, of 1.09 seconds, okay?
Dr. Mike, who cares? How fast does it need to go?
Okay, so we can plug that back into our equations for v naught, and it turns out v naught then equals 22.8 miles per hour.
What? 22.8 miles per hour? That doesn't seem like very fast. Are you sure about that?
I am very sure about that, but keep in mind that's going to be the speed right when it exits the ramp. So there's a couple things to keep in mind here. So first of all, as it goes up the ramp, it's going to slow down by maybe 5 or 10 miles an hour, okay? So we're going to lose some speed there. Also, I really didn't have the time to do the CFD modeling to actually figure out the drag and how much it's going to slow down from wind resistance. So I really don't know, but I would say conservatively we might lose 10 miles an hour from that as well. So maybe total 20 miles an hour.
Okay, so hold on. 23 miles per hour plus the 20 miles per hour you're going to live.
Yes.
Is 43 miles per hour.
Yes, yes.
So 43 miles per hour is how fast it needs to go to get 30 feet in the air.
That is my best guess, yes. And as long as it stays straight and the ramp holds up.
Okay, now that we're done with that awful and totally unnecessary explanation, can we just take a look at the Power Wheels and see what you modified?
Yes, sir.